Hi, I'm Huang, and I'm presenting a systematic study about the calibration accuracy of 3 commonly used models in extrinsic calibration problem. We mathematically derive and compare the noise sensitivity for each model so as to answer a very important question: which method is better and why? According to the sensor configuration and calibration setup, common calibration problems can be represented by 3 geometric methods as shown here. Take the first model for example. Assume we are calibrating 2 sensors called A and B. The dashed lines are the sensors' pose measurements. We want to estimate the relative transformation between the 2 sensors. For that, we need to solve an equation AX equals to B. This is easy and straightforward in this model, all because there is a reference frame common to both sensors. A typical example for this model is regular stereo camera calibration, where both cameras look at a checkerboard, and that checkerboard provided us a common reference frame. But sometimes it is difficult and even impossible to set up a common frame. For example, what if the 2 cameras share no overlapping fields of view? To alleviate this, we can introduce another unknown transformation called Y, and allow the sensors to work on separated reference frames. This leads us to the second model, with the equation AX equals to YB. Notice that both the first 2 models utilize absolute pose measurements, but absolute poses are not always directly available and can be erroneous because of drift. In this case, using relative pose over small time periods is more reasonable, and this leads us to the use of the third model, in which we replace the absolute poses with the relative ones, and the equation for this model becomes AX equals to XB. The third model is the most general model and can be used in almost all sensor configuration. Now the question is, among the 3 models, which one is more accurate? To answer this, we utilize a statistic technique called error propagation to investigate the noise sensitivity of the estimated translation magnitude for each model. As a result, we can analytically compare their calibration accuracy. Firstly, Model 1 has a good and stable calibration accuracy, regardless of the trajectory configuration, so use it if possible. Secondly, the accuracy of Model 2 and 3 are highly dependent on the rotation magnitude along the sensor trajectory. Lastly, to our surprise, Model 3 can, in theory, have a better accuracy than Model 1 if the rotation magnitude is large. I hope this work is useful to you, and thank you very much for your attention.